been quite a while since I've been back in this capacity, but I'm very excited to be here. I'm going to go ahead and get into this. I'm going to talk a little bit about Kairos and some of the lessons that I've learned from my entrepreneurial leave and going to Kairos and starting the company with my two other co-founders. We're a very mission-driven company. We start all our presentations off with our mission statement, and that's basically the Kairos Power's mission is to enable the world's transition to clean energy with the ultimate goal of dramatically improving people's quality of life while protecting the environment. All of the employees at Kairos wake up with this mission first and front and center, and it's very important to us in terms of how we proceed. It's not coming. Oh, it's this one. I'm sorry. Too many screens up here. And in order to achieve this mission, we have to prioritize our efforts on a technology that's both safe and affordable. Today's world, we believe nuclear has a lot of opportunity, but the big challenge that we see is that it's really not affordable. And so there's a lot of challenges in deploying the technology. So just a quick overview of the company. We were founded in 2016. Ironically, the day actually I sold my house here in Albuquerque, we announced we were actually coming back to Albuquerque, and we told the New Mexico Economic Development Group that we were coming here on the same day. So it was kind of a bitter day for me. We were founded in 2016. We have about 474 employees. About 150 of them are here in New Mexico at our site in Mesa del Sol. And I'll talk a little bit about what we're doing here in New Mexico. We're focused on iterative development, and I'll talk a little bit about how that happens in practice. We focus a lot on vertical integration, and that'll be part of today's discussion, is learn a little bit more about how Kairos has brought in vertical integration into our development. We're focused on a US demonstration by 2030. So we're looking at domestic deployments and really opportunities in the United States. And we're really trying to compete with natural gas, which is really setting the marginal cost of electricity today. So it's really important for us to be competitive. Really quickly about the technology, we're not going to go too deep into all the different technologies that are related to our reactor technology, but we do leverage two basic fundamental parts of our safety case, are the high temperature coated particle fuel. If you're familiar with advanced reactors, this is fuel that's been utilized dominantly in gas reactor demonstrations, and we utilize a coolant called FLI. These are really the basis of our technology. This is probably the only nuclear engineering slide that I'm going to show today, at least in terms of the details of the technology, but this is really fundamental to our safety case. It's fundamental to our technology. So in terms of what Kairos is actually doing, right now what we're really focused on is trying to deploy a technology that is really cost competitive. And so if you start on the right-hand side of this plot, really starting with cost certainty and going from the left, utilities that are looking to make decisions today about new nuclear really are looking for cost certainty. In their planning process, they really want to know if they deploy a new technology, can it be delivered on cost and on schedule? We believe very strongly that to really reach that cost certainty, it's really the product of four things. Technology certainty, will it work? It has to obviously work, it has to function as you design it. Licensing certainty, it's a very heavily regulated technology, so you have to be able to convince your regulator that you've got the right approach and the right design. So there's a lot of licensing risk for new nuclear technologies. Supply chain and manufacturing. So this is a new technology. Do you have a supply chain? Do you have the capacity really to build the pieces and parts that go into your reactor technology? And last, but certainly not least, construction risk, build certainty. That's a really important piece of really deploying these technologies on cost and on schedule. So in practice, everything we're doing right now really feeds into these four buckets. So all of our dominant work streams right now really drive, and all the iterations that I'm going to talk today about in terms of our demonstrations, really go into these four buckets here. Technology certainty, licensing certainty, supply chain certainty, and really build certainty. And we believe if you're not working on all four of these while you're developing a new reactor technology, you're most likely going to have challenges on the back end. So I mentioned iterative development. I'm going to talk a little bit about how we do this in practice. This is a slide we actually stole a little bit from SpaceX, and we adapted it really for the nuclear world. But if you look at sort of a conventional development cycle from plan, design, build, and test, if you're familiar with the big plants that have been built in the Southeast, the AP1000 projects in Georgia, really design on those activities started in the early 1990s. And if you look at the time cycles that it took to actually get that reactor technology deployed, actually up and commissioned and actually operating, you're talking about a 30-year development cycle. That's a very long development cycle from 1990 effectively all the way out to 2024. So really trying to drive those development cycles down is a really big part of what Kairos is trying to do. On the top, it kind of shows that conventional cycle, and what we've seen without the lack of really building and testing, sort of this inner loop where you see a lot of paper designs, a lot of innovation on paper, but what you're not seeing is really designs going to building and testing. And if you have a 30-year development cycle, you're waiting 30 years to get that feedback into your design for the next iteration. And so these really create a lot of challenges. There's a lot of challenges in going 30 years for a development cycle that I don't need to spend time here talking about, but that's really the paradigm that we're trying to break right now. And we do that actually in a non-intuitive way. We do it through a series of smaller iterations, and I'll talk a little bit about how we do that, but the important piece here is we get feedback into our design earlier than you would get if you're going through these larger development cycles. So how does that happen in practice? So what we do at Kairos, we focus a lot on non-nuclear development. It allows us to move actually quite quick. We've basically, we'll talk a little bit more about these projects here in a second, but we have a series of what we call our engineering test units. There's engineering test unit 1, 2, and 3. Engineering test unit 1 and 2, they're located here in Albuquerque, and I'll talk a little bit more about what those projects are. The engineering test unit 3.0, that's actually in Tennessee. And then we have our 2 demonstration reactors that we're working on right now, which are Hermes 1 and Hermes 2. So a lot of my talk today is going to be giving updates really on these engineering test units and what we're doing in Tennessee on the reactor side. Just a little bit about the company and our locations. We have a presence actually across the United States. So we're headquartered in Alameda, California. We opened up our site in Albuquerque, our manufacturing development campus in Albuquerque in about 2019. It was a very dynamic time. Unfortunately, the pandemic hit right when we actually announced we were going to buy the property, and that created some challenges in terms of early staffing. We had plans to bring people out to California, really for a lot of knowledge transfer. Obviously, the inability to travel during the pandemic created a lot of issues. We're developing a facility at Los Alamos National Lab to produce fuel for the Hermes 1 reactor, and that's at what's called the low-enriched fuel fabrication facility. And we have an analogous facility right here that you can see where we're doing effectively fuel development, but not at the scale that we would want to do in Los Alamos. We have a site in Oak Ridge, Tennessee, where we're building the Hermes 1 and Hermes 2 plant. We started construction on the Hermes 1 reactor, so that work has already started. We have a small licensing office in Charlotte. We have an instrumentation lab in upstate New York, and we have a facility at a partner called Materion, which is actually where we produce our coolant FLIBE at scale. So that's an important location for us where we produce our coolant. So I mentioned vertical integration. Really, the vertical integration that we've been focusing on, it does include some of our major work streams. So fuel and salt are really important to Kairos. That's very important to our safety case. It's important to making our reactor work. So we've made commitments to bring in salt production as well as fuel production. So those are commitments that we've made. These are just examples. I mentioned the site that we have in Elmore, Ohio. That's where we're able to produce metric ton quantities of FLIBE that we need for our reactor demonstrations. And this is a picture of that FLIBE actually arriving at our site in Albuquerque. These are actually containers that contain about 2 metric tons each of FLIBE arriving from Ohio. In addition, we have a lot of work around fuel that I mentioned earlier in our partnership with Los Alamos. We have a pebble development lab where we produce pebbles, and effectively we're standing up a TRISO development lab where we have a state license and we work with effectively natural uranium and depleted uranium. So it enables us to iterate very quickly and bring in design concepts into the fuel form itself. In terms of manufacturing, a lot of what Kairos does, about a quarter of the company is actually in manufacturing, so we have a very big manufacturing presence. We hold an ASME stamp for Section 8, so we're able to do vessel production. We set up a lot of this capability with actually a lot of local hires. It's been a great process in terms of standing up the manufacturing. So in terms of manufacturing capabilities, we've stood up a lot of both milling and machining capabilities, milling and turning capabilities at our site, and that's shown in the upper right. Picture up there, we have a pretty substantial welding team. We brought in vessel manufacturing. That's an area that we've been focusing a lot of our attention on. We will be producing our own reactor vessels as well as vessels that support the overall technology. And in the lower right, I'll talk a little bit about it. We have graphite in our reactor as a moderator. It's a very important part of the design. The graphite machining is a capability that we've also invested in and standing up. So there's a lot of manufacturing activities that are happening down in Mesa del Sol. It's effectively where we do our large-scale manufacturing. It's where we do a lot of our large-scale testing. To talk a little bit about a commercial agreement that was announced. We have an agreement with Google that was signed recently. You may have seen the news around that. There's been a big push from the hyperscalers and a lot of interest in AI power demand challenges. And so we have a partnership we're very excited about with Google. We've assigned a master plant development agreement that really creates the right framework for us to be able to set up power purchase agreements with utilities and regions that Google is trying to service. So that's a process that we're going through now. And we do, oh great. And we do plan to have some, whoa, that's pretty loud. We do plan to have some news that will be coming out in the public domain relatively soon. But this is an agreement that allows us to work through the commercial case on the back end, which is really important to us. Here's some additional information around the vertical integration part. These are just some of the pieces and parts that we are focused on. On the left-hand side, you can see some of the nice manufacturing activities. I'll talk a little bit later about the vessel manufacturing. This is rolling plate here. These are pieces and parts that go into key parts of our reactor system. So just a lot of manufacturing and a lot of focus on effectively building and demonstrating the technology. These are just pictures of the fuel production line and some of the pebbles that went into our first engineering test unit. And then we talked a little bit about the fly production. This is a facility that we just broke ground on in Mesa del Sol. It's called our salt production facility. You can see it here a little bit, but we just started construction on it. This is the place where we're actually going to produce the enriched fly that we need for our reactor in Tennessee. So this is a big project that we have ongoing, and it's really setting up the capabilities for us to be able to produce fly at scale. An important thing to take away is even though the Hermes 1 reactors in Tennessee, many of the pieces and parts that make up the primary system actually come from here in Albuquerque and are fabricated here. So a lot of the manufacturing activities are actually supporting that deployment in Tennessee. So I'm going to talk a little bit about these major iterations. What is Kairos actually doing? We're trying to demonstrate our technology through these iterations. The first one that we built, this facility was run. We've actually decommissioned it and it's been moved out of the current location, so it's no longer with us, but I'm going to talk a little bit about it because we got a lot of lessons learned from it. Why did we do this demonstration? I mentioned we do non-nuclear testing. This is not a facility that's regulated by the NRC. It's a facility regulated by OSHA and EPA and obviously local permitting authorities, but it's not regulated by the NRC. It doesn't have nuclear material in it. It's effectively mock-up material, but it performs mechanically very similar to the reactor system. The three areas that we were focusing on was really to evaluate our supply chain. If we didn't have a supply chain that can make a mock-up of what we were trying to do, then we knew they couldn't deliver for the reactor system. So evaluating the supply chain was really important to us. It also enabled us to build really an organization that was able to do the design, test, iterations in-house in a very efficient way. So that was also a very important objective for the ETU-1. And last but not least, once you actually build the facility, running a 24/7 facility like this and getting the operations back into the design, again, very, very critical for Kairos. So again, if you remember my earlier slide where we talked about technology certainty, licensing certainty, supply chain certainty, and construction certainty, these are examples of how this kind of feeds into our development. So the engineering test unit 1, got some pictures here. I'm going to kind of walk through some schematics, or sorry, some pictures of the actual build. As I mentioned, we took the property over right at the beginning of the pandemic. So a lot of this work was happening during that time period. This is all in Mesa del Sol. So this is when we acquired the shot, what's called the shop manufacturing building down in Mesa del Sol. The first thing we did was we actually added an annex. It's a beautiful building, but it's actually got a very low high bay in terms of the roof height. So it creates some challenges for doing larger scale tests like what we're building. So I'm going to walk through some pictures that show the engineering test unit 1 in Albuquerque and just kind of show the sequencing of the build. So this is what we call our ETU annex. It's now where we do vessel manufacturing. It's a 40,000 square foot pre-engineered metal building. It's what housed our engineering test unit 1. This is a picture of the vessel that arrived. I mentioned we brought in vessel manufacturing. This vessel was not produced in-house. It was actually an external vessel. When it arrived, we had some tolerance issues with it, and so we actually had to do a fair amount of machining of the graphite that had to go into the vessel. It was actually a result of this experience that we made the decision to bring vessel manufacturing in-house. So this is a picture of the vessel about to be lowered and placed into its location in the enclosure. This is showing the heaters coming up around it and the interconnecting piping, the large bore piping where the fly flows through, and a lot of the support infrastructure around the vessel. Moving forward to March 2022, this is some of the actual supporting infrastructure. You can see the upper head of the reactor vessel is located here. And it's important, this is at a very equivalent scale for our Hermes 1 reactor. So this is a like-for-like scale in terms of physical dimensions. Moving forward to August of 2022, you can see more of the upper head equipment has been installed. In the upper region, you've got insulation going up around all of the piping and the vessel, and you can see more of the facility coming together. And this is the final picture of it prior to operations, actually post-operations. We self-perform a fair amount of the work that we do. Certainly for assembly of the engineering test unit in the upper right hand, you can see some of our team members actually installing the graphite blocks in the reflector structure within the actual vessel itself. In the lower right, you can see FLIBE actually arriving. Again, it's about 12 metric tons that we loaded into the engineering test unit 1, which is a pretty substantial amount of material. We have 2 control rooms. We have one in Albuquerque and we have one in California. So we're able to do remote monitoring from California as well. This was a big change for Kairos. We're not a 24/7 operations company, but when we started up ETU, it became very clear we would have to run this facility 24/7, and we had to do it over several holidays, and this was a big shift for the company, but it actually it created a lot of opportunities to build up the operational program that we're going to need for our reactors. So what are some of the lessons learned? I mentioned really from the ETU1, we had some tolerance issues with the vessel as it arrived, so that was a major lesson. It's also if you look at reactor installations, the vessel is a very central part of the construction process, and so not having your vessel early is a challenge. It's also one of the last components you want to design. So there's a lot of tension between trying to get the design complete and having the vessel arrive. Because of the out-of-tolerancing issues that we had with the vessel, we actually had to remachine all of the graphite blocks. There's about 308 graphite blocks that make up the reactor internals here. We actually had to go back and actually remachine all of those graphite blocks, which was a big deal for us, but because we had that capability in-house, we were able to do that relatively efficiently. A lot of positive experience about the pump. So this pump was actually a pump that we worked with a company called Barber-Nichols to develop. We brought a lot of that technology and capability in-house, so the pump that we're building for the ETU2 is all built within Kairos proper. And then last but not least, we learned a lot about the value of modular build. We were not able to do that for the engineering test unit 1. We were forced to do some modular builds just due to the schedule and how it played out, but it really pushed us in a direction for engineering test unit 2 to really incorporate modular construction into the construction process. One of the major lessons I would say is getting a complete design and getting a facility like this through the finish line actually takes a lot of work. There were many times that we were at 90%, and we were at 90% for a long time. The reality is getting the design complete has a lot of major challenges. And so when you look at nuclear construction today, one of the things that they will always say is you need to have the design complete prior to starting construction. In practice, getting to a complete design has a lot of challenges. So this was a very important process for Kairos to kind of get to that final finish line on the design, but that was a very valuable lesson for us in terms of not being too optimistic about schedule and ensuring that you have the ability to deliver. This is just a little bit of information about ETU1 in terms of the numbers. It's a high temperature system, so it operates normally around 600 degrees Celsius. These are just some of the capabilities that were demonstrated. We like to say it's the world's largest FLIBE system that's ever built. The other large FLIBE system that we can look to is really the molten salt reactor experiment that was built in Oak Ridge, which had about 4.5 metric tons. So this is at a pretty substantial scale in terms of the new application and the new environment in terms of the actual tonnage of the salt. We have a system where we insert pebble fuel, so it's online refueling. The ability to demonstrate that capability was really important for us, so we were able to go through that process of loading fuel in and removing fuel. We were able to push the pump to very high flow rates, so get confidence in how the pump behaves. We do have a mock reactivity control system. It's actually all the same equipment that you would use to, in an actual reactor, but of course we're not controlling reactivity, but we're able to see the mechanical insertion, how it performs and how it behaves. So we had about 25,000 strokes of that system. And then also chemistry control for us is really, really important. The ability to actually demonstrate chemistry control and actually show the ability to take samples and to be able to monitor, those are all really important steps for us. And it's very difficult to do that for a first-of-a-kind reactor system. If you can do that in a non-nuclear environment, you can demonstrate a lot of those capabilities. And last but not least, we had to go through the full life cycle of actually decommissioning the facility and removing it and cleaning it in a very responsible way. And you can see on the lower right, that's actually a picture of the vessel leaving the facility. That's really important to us. We're going to be building a reactor that we're responsible for the D&D of that facility. And so getting lessons into how to look into decommissioning these facilities, even though this isn't a rad environment, it's a beryllium-bearing salt, it's still a very highly toxic environment. And getting those lessons have been very important for us in terms of driving costs down for the Hermes 1 reactor design. So I'm going to talk a little bit about a new test that we're building right now, which is called the Engineering Test Unit 2. This is an activity that we're doing right now, and again in Mesa del Sol. Why are we doing it? Well, we're basically, there's about 5 of the reasons that are listed here. 4 of the reasons listed here. We have very strict cost targets that we're developing this Engineering Test Unit 2 under, really related to sort of the 80% of the cost coming from commercial off-the-shelf items and raw materials. So that really forces our team to have to leverage our manufacturing capacity, and that's been very critical for us, better leveraging our manufacturing capability. Demonstrate some more features of the actual Hermes 1 reactor system, so how we can actually start up the reactor. That was very critical for us. In particular, we were looking at also capabilities around upper head maintenance and things of that nature. One of the big features for the ETU2 that we've been adopting is really this modular design concept. And so a lot of the Engineering Test Unit 2 is actually being built in a facility next to the enclosure that I showed you earlier, and that equipment's going to be brought in as it's being readied. And then last but not least, every FHR that we operate as a company will actually start off as an ETU. It'll start off in an environment where you're introducing effectively non-nuclear fuel, and then you will add nuclear fuel as you go. So all of our reactors effectively have to operate in this environment prior to actually doing our pre-critical and zero power testing. So we're actually able to bring a lot of that test program into the ETU2 and demonstrate how we're going to start up Hermes 1. So that's very critical for us in terms of developing procedures and how we would actually start up the reactor system. So where are we with the Engineering Test Unit 2? Very pleased. We got our vessel installed earlier this year in January. This is a picture of the team. This was a vessel that we did entirely in-house. We have a milestone for our DOE program that we had to install this vessel. We hit the milestone of January, so that was really important to us. And this is just a picture of the team very proudly showing the vessel prior to insertion over here. Plate comes in, it effectively gets rolled. There's a whole process, of course, around machining and welding the vessel together. And then the installation is shown here on the right-hand side with a very proud team that finally got the vessel installed. So we're building out this facility as we speak. Got some more pictures that show, I mentioned, we're doing this in a modular build fashion. So we have our modular system facility that is adjacent to the enclosure. There's about 32, 33 skids that make up the Engineering Test Unit 2. And so by doing this in a modular fashion, we're able to actually build out the facility next to the facility while we're doing the decommissioning work that I mentioned earlier. This is an approach that we're going to utilize for Hermes as well. So we'll be able to send similar equipment to Tennessee, here from New Mexico, to go be installed into those reactors in Tennessee. And so really the lessons from ETU2 are going to inform the construction of ETU3 and what we're doing in Oak Ridge, Tennessee. So this is just a quick picture of what we're doing here in Tennessee. There's not much to show, at least right now, because we're still in early construction. The Engineering Test Unit 3 is effectively a construction mock-up area for us. It's an area that we can actually learn a lot about the construction that's needed for nuclear construction. We can bring those lessons really from the commercial construction and bring them forward in the nuclear environment. I'll give you an example of that. We have 73 drill piers that make up the foundation of our ETU3 building. A little schematic of it shown over here. It's actually bigger than our Hermes 1 reactor building, so it's a pretty substantial structure. The drill piers and the contractors that we're using for this work are the same. It's the same technology and the same contractors that we're going to be using for Hermes, and the nuclear safety related construction. So this has given us effectively, there's 73 drilled piers, 73 lessons in terms of how when we go into the nuclear construction for how we build Hermes, we can bring those lessons learned into that environment. That's really important for us. Having effective quality control is absolutely essential for nuclear construction, and getting those lessons from commercial construction, then bringing them into the nuclear environment early has been a really big win for us. We're going to be building effectively a lot of the upper head components that go into the reactor in this building over here, which is really where the ETU-3 is going to be located. We plan to install that vessel in May, so that's what the team is working pretty closely on. We're not actually fabricating that vessel, but we'll have some announcements about what we're doing in Engineering Test Unit 3 here pretty shortly. But this is a capability we've gotten started on in Tennessee, and this is really the precursor to the Hermes 1 construction. So I'm going to talk a little bit about the Hermes reactor itself. This is a nice artistic rendering of it. As I mentioned, we are starting with the commercial construction for our ETU-3 on the drilled piers, but we have done excavation for the Hermes 1 site. So we've completed excavation. That's been a pretty substantial challenge. The site we have in Tennessee, it's a beautiful site, but it's also the site that was where the K-31 and K-33 enrichment facilities were originally located. DOE spent a lot of money actually cleaning up the site and preparing it for companies like Kairos and others to be able to come in and leverage that site appropriately. One of the challenges is that we actually had a fair amount of that K-33 enrichment facility had footers and duct banks that were actually located underground, that when DOE actually removed the original building, the subsurface components were still in place. So when we did the excavation, we actually had a lot of work managing, removing that material responsibly. But we got through that, and we'll be starting drill pier construction here for Hermes 1 in about 6 weeks. As I mentioned, licensing is actually a very important part of what, again, licensing certainty is absolutely critical. This is just a quick schematic that kind of shows how Kairos has approached licensing. We've had a lot of early engagement with the NRC through what we call pre-application and issuing topical reports. You can think of these as sort of, if you're writing a dissertation and you've got 5 chapters in your dissertation, getting your professor to look at each chapter before you submit the whole thing. It's a sort of a similar kind of concept and idea that they're able to look at those really topical report sections and issue what are called the safety evaluation report. That allows us, when we submit our construction permit, to be able to have a lot of that licensing risk de-risked and get those insights into the licensing package. So that's been a big part of what we've been doing. This just shows some of that engagement, and that's been going very well to date. In terms of what we've accomplished on the licensing side, we have construction permits for both the Hermes 1 reactor and the Hermes 2 reactor, which will enable us to effectively start construction. As I mentioned, what Kairos is doing, it's a little bit of a change from the historic, the old historic approach was always what we call a 2-step process. There was an effort to make it more streamlined, to make it what we call a Part 52 process. That had a lot of challenges in its implementation, actually, with that big project I mentioned in the Southeast in Atlanta. And so Kairos has adopted that 2-step process. A lot of the developers today are going back to that 2-step process. And what that basically means is you submit a construction permit, which allows you to start construction, and then you submit an operating license application to be able to run the facility. So there's 2 steps in that process, but it does allow you to start construction, especially early on. And so this is a big part. This shows just kind of some of the highlights here. We've issued 12 topical reports, and we've got obviously those 2 permits. This is a really big part of getting the licensing certainty that I was mentioning earlier. So I'm going to conclude here. I think 35 minutes was roughly where we were going for. Just some kind of key lessons learned and observations. Obviously leaving from an academic environment in a great place like UNM and going into a more commercial environment and learning how to do things a little bit differently, there's been a lot of lessons that have been taken away. And these are just some of the key lessons that I kind of been thinking a little bit about and kind of writing down. So, the right strategy is essential, but the biggest challenges are in the execution. So that nice chart I showed you earlier, it's pretty easy to put that together, but in practice, delivering these installations takes a lot of work, and the execution is really critical, and that's very important for Kairos. I would say the hard things are often easier than people think, and the easy things are often much harder than people think. When we vertically integrated, we heard a lot of people say, don't do that, don't do that. The reality is it is difficult, But a lot of the things that people said were hard were not impossible, and they may not have been as hard as they were. On the flip side, I would say things that we thought would be easy, hiring, bringing certain folks in, finding the right talent, actually proved to be quite complicated. So I think a level of humility is important. I think this is probably pretty common for a lot of ventures and new startups. The balance between speed, creativity, and structure process is a constant struggle. It's a challenge, and I would say one of the things that Kairos has tried to do we focus very much on is to have an organization that's quite agile. And that can be very difficult when you start to get a company of the size of 450 and so. So that can create a lot of challenges. Not the last thing, but I would say engineering within a vertically integrated company is actually very different. A lot of times the interfaces that you would see in an organization that may be a design organization would be with external manufacturers, external suppliers. A lot of those people are in our company, and so it's a different relationship that you have. It creates different opportunities, different synergies, but really a lot of good manufacturing can solve a lot of problems, especially for our design team. So having that capability is unique, but it is a different way of operating. It's a different way of actually running a company. When doing something for the first time, flexibility and schedule is important, and that is not unique to a research environment. Of course, when you're doing first-of-a-kind work, it's very difficult to predict with high certainty how long things are going to take when you're working through very difficult problems. So we push pretty hard to have a more agile approach early on. It's challenging to implement that. People want to work with very steady schedules and committed programs and providing that direction. But when you're trying to do first-of-a-kind work, I mentioned we stood up that molten salt production plant. Getting that capability online, it's a first-of-a-kind facility. We're doing it at a partner's location with new challenges. That all introduces risk into the overall program, and having that agility is actually really important for us. Whenever possible, simplify the problem and start small. That kind of feeds into how we do our what we call our little loops, how we can do development quicker. We try to not trivialize, but we try to reduce the problem in terms of the types of problems you're trying to solve. So, for example, we do a lot of this on the manufacturing side. We call the manufacturing little loops. I showed you that very large vessel. If there are certain features that we want to be able to look into, we can do certain manufacturing demonstrations at much smaller scale. There are distortions when you do that, but if you can manage those distortions, you can get a lot of insights into that process and you can piece that together. And so it allows you to move quicker. It allows you to actually move faster in a way that can be very challenging when you're looking at very large integrated engineering projects. And last but not least, really embrace the fact that no one cares about our success more than we do. Controlling your own destiny is a very important, I think, takeaway. Oftentimes in this space, you may be looking for important partners that can carry you forward, but the reality is having really control of your own destiny has been really critical for Kairos. So that's been a big part of our identity and DNA. I'm going to mention a little bit on the opportunity side. We have an amazing number of employees at Kairos in our KP Southwest facility that actually come from UNM. Even though we're a nuclear company, we hire all engineering disciplines. As I mentioned, a lot of our base here in Albuquerque is manufacturing oriented. So we are looking for chemical engineers. We are looking for civil engineers. We are looking for nuclear engineers. We are looking for people that come from the FSAE program here, people that have had experience building things and seeing projects all the way through. It's a bit of a misnomer that we're only looking for nuclear engineers. We need nuclear engineers, so don't take that away. But we really do need all of the engineering disciplines, and that's really important to us. So if you're interested, I'll be here afterwards if you've got any questions about opportunities. We've had a lot of success from students here that have gone into our program as interns that are now turning into leaders that are running pretty substantial parts of our program today. So we've had a lot of good luck there, and we would like to continue that to the degree that we can. So with that, I think I'm open to take some questions now, and if there's any comments. Yes?
Hello, Blanford. My name is Alex Soto. I'm a nuclear engineering senior here. You said that you'd be moving vessel manufacturing into the Kairos operational, branches. Is that also motivating you guys into looking into shielding materials as well?
Sure. Yes. So absolutely. So the short answer is yes. Just to clarify, we've stood up the vessel manufacturing capability, and we're utilizing it right now. So that decision's been made, and that's work that's actually happening here at our campus down in Mesa del Sol. In terms of shielding, absolutely, those are areas that we are looking into. This is largely around the equipment that makes up the reactor system in terms of the manufacturing footprint that I talked about, but there's obviously a lot of costs in the civil structures that surround the reactor, that make up the reactor building, that house the reactor itself. There's a lot of opportunity to drive down costs, and that's also where a lot of the shielding costs will come in. So we are interested, and we are looking into those types of opportunities. Yes?
Hello, sir. I'm Kaylin Pashota. I'm just wondering, why a molten salt reactor over like a water one?
Sure. Why are we doing this crazy thing? Water, there's a long history with water reactors, light water reactors. All the electricity that's produced today from nuclear in the United States comes from these technologies. We see a unique opportunity. I'll just maybe quickly go back to the first slide. What we see is an opportunity for a low pressure system. So one of the nice features of this coolant is even though it can operate at 600 degrees Celsius, it operates at low pressure. And so that creates a lot of opportunities in terms of the safety case. So having a very high performing fuel like triso fuel with fluoride salt, it actually enables us to have a little bit more of a unique, what we call a safety case. So in licensing space, we've been successful in actually pushing arguments of the NRC that have limited what we call the safety related components that make up the primary system. You really can't do that with a high pressure water system. And so this, we believe, creates a lot of opportunity. Now there's a lot of cost in standing up this fuel and this coolant, so that creates a new challenge. But what it does create is it creates actually a unique safety case for us to actually long-term drive down the economics that go into the plant. So that's really important to us. And by having a low pressure system, we're able to actually remove certain accident sequences that you might see in some of these technologies that are operating today. And those are operating very safely today in a very efficient way. And we need large gigawatt light water reactors too. I would also argue in a weird way, by not being tethered to historical nuclear technology. So for example, if we were to go build a gas reactor or a sodium reactor or a light water reactor, there's actual plants that have operated with those technologies, of course, and that kind of drives you actually into a certain mindset and a certain approach. In some ways, and it's a little bit crazy saying it, by not having that historical precedence, I mentioned there was a molten salt reactor experiment that was built in Tennessee. We're not tethered to a lot of those philosophies and approaches and vendors and ways of doing business, which has actually created a lot of opportunity for us. In a weird way, it's sort of because there's not been that history that's kind of driven you in certain arguments or certain approaches, it's actually opened up a bigger design space for us and a different development space, if that makes sense. Yeah.
Very, very interesting kind of accelerated development. I'm just more curious about the initiation of this project, since at the time when the company was formed, it seemed like there were different fluoride-based coolants under consideration. You made a selection of a certain coolant with all uncertainties at the time. Could you just describe a little bit the history as to why you choose that particular coolant?
Sure. It's a good question. Our coolant does require enrichment in lithium-7, which is a unique feature of the coolant, and that's something that is unique to the technology. We selected the coolant largely for its nuclear properties, if that makes sense. And so we're for our technology, we don't want to produce tritium. We're worried about excess tritium production. For fusion reactors that use FLiBe in their application, they want to produce tritium. So they have the opposite problem they're effectively working through. But largely the selection of FLiBe was really driven by the nuclear properties from our standpoint. And it's really the combination of these two that really provides that safety case. There are other coolants out there. There's chloride salts. There's other fluoride salts people are looking at. We've gone around and round on reevaluating, looking at different options, but we keep coming back to FLiBe really for the nuclear properties. Yes?
Yeah, so on the subject of the coolant, I worked at beryllium for a long time, so to handle tons of that without exposure is really impressive, so congratulations for that.
Thank you.
But what I wanted to ask is, you mentioned supply chain issues, so you're going to be needing a lot of HALEU and enriched in the other way of the lithium. Could you talk about that just a little bit, particularly the HALEU?
Sure. So HALEU refers to fuel that's enriched up to just below 20%, so effectively 19.75%. There's nothing technically challenging about it. There's just not the infrastructure today to actually deploy it. The U.S. government has spent a fair amount of money, or is planning to spend a fair amount of money to stand up that capability. Historically, HALEU could be procured from Russia, but there was a ban on procuring that enrichment. Who knows what's happening? I won't even get into any of that. But what I will say is for the Hermes 1 reactor, we need smaller amounts of the HALEU. There is material that's available within the DOE complex. They have a program where they're trying to get that material available. So they'll be making announcements about that, we hope, soon. So that will cover us for Hermes 1. For Hermes 2, we will need more fuel, and that will create some challenges. We can run these reactors on 10% enrichment, so that is an area that we are looking into, and 10% enriched material is available. So those are options that we're also looking into now. We will need that capability to be stood up. That will be important for us to have a supply for HALEU. The U.S. government seems committed to developing it and pushing that forward, but that is risk in terms of one of our supply chains. And then you asked about the enrichment. We need enriched lithium-7 for the coolant. That's important for the technology. That technology is something that we've developed and we're implementing at our facility. It's held under our trade secret program, but that is a capability. It's chemical enrichment, so it's not a nuclear process, it's a chemical process. But that's a facility that we're developing, as I mentioned, in Mesa del Sol, and it's a capability that we're putting in place. Yes?
What's the duration for fabricating the pebbles or the coated particles?
Sure. So really there's three components to the fueling concept. So you've got your kernels that are sort of the inner part of the particle, and they're surrounded. This is the particle, and then there's the fuel form, which is the pebble form. The work that we've done in our facility in Mesa del Sol is use surrogate TRISO to date. So it's a little bit of a misnomer in terms of the amount of time. Let's see, we were producing about 300, at our peak, we were producing about 300 pebbles a day for the non-nuclear pebbles. So that's just pressing graphite pebbles. I don't have a full answer for you for soup to nuts. When we get our TDL facility up and running, we'll be able to inform that more. But that is an important part. As the schedule gets compressed, we do have to find ways to deliver the fuel faster. That's where these capabilities actually are really, really important for us. So for the engineering test unit 1, we had about 35,000 of these pebbles. All 35,000 were hand pressed by our technicians, hand pressed. And we developed actually automatic pressing capabilities to be able to accelerate that process. That's really important to us because we have a pretty small facility at Los Alamos that we'll be putting our equipment into. So to be able to get more production and capability out of it, it's really important for us. Yes?
Maybe just coming back again to the start of the company, to which extent came IP out of the university system into the small startup?
Sure. So Kairos' position on IP is a little bit unique in the sense that we believe our technology is relatively novel enough and we're moving fast enough that spending a lot of time filing hard IP and patents and things like that has not been a focus for us. So we don't have a very large IP portfolio. It takes a lot of effort to file those patents, and then your engineers are now filing patents instead of doing development and moving things forward. So we've not had a strong focus on IP. There has been some IP that's been developed at the university. Some of it has been leveraged, certainly for the work that we've done here at UNM. That IP is less applicable because it was for a different design at the time. But there's really not a lot of incoming IP that we've been overly concerned about, if that makes sense. But it is part of our strategy around protection, if that makes sense. We do have trade secret activities around the fuel and the salt, which are important to us, but those are not in the visible sphere, if that makes sense. Yes?
Can you comment on the environmental impact of this technology compared to other technologies and how you can sell it to the general public?
Sure. So it's a good question. Kairos is very committed to environmental stewardship. It's really important to how we do things. It's actually been part of how we select sites. So the ability to go to a former, basically an enrichment facility site that was contaminated pretty heavily, to be able to repurpose it and use it for this application really fits into our environmental mission. The short end of it is you have to manage these hazards appropriately. So when you mentioned the beryllium handling, that's relatively novel, actually. There's a lot of work, especially in this state, with beryllium machining, managing beryllium, but it's usually in a metal form, where you're working with it in basically a metal form doing machining work, and you're generating aerosols and challenges like that. We're unique. It's a beryllium salt, so it's actually in a fluid form, and it's at a high temperature, so it's a little bit different in terms of the hazards. All those hazards have to be managed appropriately. We obviously cannot have releases. The big win for this technology is carbon-free emission and basically carbon-free electricity. That's the big win on the back end. And we believe these types of technologies can be deployed faster, and they're more deployable because of the size and the way that the projects are being structured. But really the long-term environmental benefits are really around our ability to actually deliver carbon-free technology, if that makes sense, or electricity on the grid. That's a big part of what we're doing. We have to demonstrate that. That's a big part of what we're trying to do through our program and show that we can hit our cost targets. From a waste perspective, we do have slightly less waste, but they're still going to require ultimate disposition of our waste forms, and that's a problem that's going to remain regardless of what Kairos does or not. So that's a problem that the United States has right now. We've got stranded waste over all the sites that are operating today, and we have to develop a national solution around that. Our technology doesn't solve that problem, but it doesn't make that problem any worse, if that makes sense. Yes?
I'm curious about the triso fuel. What's the approximate lifespan of the pebbles? What's the recyclability of the material?
Sure. So if you're familiar with like gas reactors, their fuel form, the pebbles are billiard balls. Ours are ping pong balls. So just in terms of spatial scale, we do have higher power densities in these reactor systems, so they do go through fewer times. We're able to reach higher burnups with the fuel. Those are all dials that we're able to kind of play a little bit with in terms of the commercial application, if that makes sense. So we have basically a discrimination capability. When the pebbles come out, you're able to measure burnup in the pebbles and determine whether they need to be dispositioned or go back into the reactor. Nominally, each pebble goes through the core about 6 times, I think is the number, and it's very, very slow flow. It takes a very long time for the pebble to go from the bottom of the core all the way to the top. So it actually takes a fair amount of time. The exact lifespan I don't have off the top of my head, but that gives you a rough feel for the passes and how long it would sit in the core. Carl.
Yeah, thank you for coming, Ed. Really appreciate it. I'm wondering if Kairos is thinking about other uses of this reactor besides energy production, such as medical isotopes, things like that.
Right now, we are focused predominantly on electricity. It's very difficult for companies like ours. You can get very spread across a lot of different initiatives. One of the neat things about Kairos is everybody's really working on one project, one delivery. We don't have a space nuclear group, a group doing big reactors, a group doing small reactors, kind of chasing federal dollars. We're very focused on the delivery here. Quite frankly, Hermes' one primary mission is to demonstrate we can do nuclear heat in a cheap and safe way. That's the big mission. If you can get through that process, nobody doesn't believe you can't build a steam cycle that could connect to it, but it adds a lot of complexity, of course, when you go down that path. So people want to see you can control the costs on the nuclear side. If we're successful in going down that path, it will open up other opportunities. There's a lot of opportunities for process heat at our temperatures, a lot of opportunities to not just do electricity production. The nice thing about process heat is it actually simplifies what we call the conventional island and sort of the back end of the plant in terms of what you would need. So there's a lot of advantages to potentially going down that path. Right now, we're pretty singularly focused really on the producing cheap nuclear heat, then how that fits into our Google commercial agreement, which is really around electrification. Longer term, though, if we're capable of delivering these systems at very affordable cost targets, it will open up other opportunities, we think. But right now, we're really focused on electricity. Yes?
Should we have to consider about the HF gas when we use the fluoride stuff as a tool?
Yes. Yeah, so HF management's very important. That's a big part of operating the plant as well.
Yeah, so how could you like keep like a good still like a long-term operation during because you said like 600 degrees C?
Yeah. So for the ETU1, we had HF management. We have a scrubber system that's able to manage HF, and that was a big part of our operational program. But we do have to manage HF appropriately. Yes.
When you get the production version going, how big would it be? I mean, how big a building would it be?
I'm sorry, I can't hear the first part of your question.
When you get your production version finally built, how big of a building would it look like now?
The reactor building itself, well, the Hermes 1 reactor build is approximately 30,000 square feet. For our commercial plant, I would argue it's going to be on the order of about 50 to 60,000 square feet, at least the primary, what we would call the primary reactor building. That's not the full plant, but that would be the equivalent of the reactor building, if that makes sense. That's just for rough scale.
And how is your cash flow going versus what you projected?
That's a good question. Well, this isn't the best place to talk about that, but I will just say we have committed projects and we're moving in that direction. So I wouldn't say it's not a concern, but it's not slowing us down at this point. Yes?
Sorry, Glenn, for one more question, probably to address the elephant in the room. How do you feel like this current administration is feeling towards, or how are the vibes towards nuclear technology?
Okay. That might be the hardest one. Well, I think going back to the second George Bush, there's been bipartisan support pretty generally for nuclear for actually quite some time. It's been increasing as you go through the different administrations. The Biden administration was very pro-nuclear. I think the Trump administration is also very pro-nuclear, and we've seen very positive signs. The Secretary of Energy has recently visited a lot of the labs, New Mexico last week, and Tennessee as well. And all the signs that we're seeing and hearing they're very positive on nuclear. I think there's other clean technologies that are kind of in the crosshairs right now, but nuclear kind of straddles the bipartisan interests, and there's a lot of strong support for nuclear. So from our standpoint, we hope and we see a lot of strong signs that will continue into this administration. But what we're seeing on the federal side and employees could create challenges with the NRC and other agencies that we work with. So those are kind of tangential but pretty impactful impacts that may create challenges downstream. But in terms of the technology and supporting nuclear, I think we'll see bipartisan support moving in that direction under the new administration as well. But who knows?
Thank you.